Hey everyone, I want to welcome you to a brand new series that SKALE is bringing to you. It's called Math for the Impatient. Basically, it's going to be an ongoing series of conversations about math with our co-founder and CTO, the SKALE co-founder and CTO, Stan Kladko. And essentially think of it as the math that you get when you don't want to bother getting a PhD. So Stan, if you want to just give us a quick background on yourself, since this is our first shot, it'd be great.
Yeah, thank you, Marcus. I'm Stan Kladko. I'm the CTO of SKALE, but in my former life, I was a scientist and I have a PhD in mathematics and physics. So we are really excited to have the series to explain how science, in particular how mathematics, helps blockchain.
Cool. I figure we can start the series out with something super easy because I think in general people want to start easy. So the first topic is going to be threshold encryption technology. We're going to talk a little bit about how SKALE is going to be looking at using threshold encryption technology and how it can be used to solve some of the problems around front running and MEV. So I think first of all, let's just get an understanding of what exactly is front running and MEV.
Yeah, thank you, Marcus. So front running and MEV, actually, those things are really easy to understand. Front running is something that existed in history long before computer science. The simplest example of front running is, let's say you want to buy a ticket to your favorite music band, or maybe to get to your favorite soccer match. So you want to buy this ticket, you go to the ticket office, and then what you find out that someone already bought this ticket and offering this ticket to you at a higher price. So that's a really simple idea that if someone knows some information about you, in particular, if someone knows that you want to buy something, then this someone can trivially benefit but buying the same thing and then reselling it to you. So that's the idea of front running, and it existed in the human civilization for a long time. But it turns out it's really widespread on the blockchain today. In particular, it's widespread on all kinds of DeFi applications, such as decentralized exchanges, Uniswap, SushiSwap, other decentralized exchanges. And what happens on those exchanges is that if you go and you want to buy a token, someone actually is buying this token in front of you and selling this token to you at a higher price. So what ends up happening as this person is benefiting and you are ending up paying price, which is higher than the market price. Turns out that people are now making hundreds of millions, if not billions of dollars per year by just doing these front-running attacks. Now, all kinds of DeFi applications have these front-running possibilities, and I just described the simplest one, but you can go in all kinds of details for different DeFi protocols. What's important is basically every time you are trying to do anything on blockchain using DeFi, someone can use this information and benefit and actually take part of your profit or part of your money. So that's pretty much front running. Now, the most natural person to do front running is the miner, because as we all know, the miner is the person, the entity that actually assembles transactions into a block. So if you're sending your transaction, this information is actually obtained by the miner, and it's trivial for the miner to put another transaction just in front of your transaction, or maybe sell the right for this transaction slot to some different party that does front running. So now there is a thing which is called miner extractable value, MEV, basically meaning that miners not only getting the regular blockchain fee for creating blocks, but also doing either front running themselves or reselling the front running rights and actually making very significant money, basically using users as a profit for this money enterprise. So basically front running and MEV are pretty big problems. And what we are going to discuss today is a technology which is called threshold encryption. and that this technology, how this technology helps to protect against front running.
Yeah, I think that's great. So that's a good segue into moving into an explanation. What exactly is threshold encryption technology?
Yeah, and this is actually really, really interesting. First thing is that people are trying to use all kinds of things to protect against front running and to protect against MEV. There are all kinds of technologies that are being used. The beauty of threshold encryption is that it allows to totally avoid front running and MEV. And in addition to that, it doesn't require any modifications to the blockchain, in particular to the Ethereum blockchain that we run at scale. So you can keep on using your Solidity programming language, the actual source code of your DeFi application, the way you deploy it, the way you use it. Nothing really is changing, but magically the application starts to be protected against front running, and protected in the absolute mathematical sense, meaning that it's actually possible to prove mathematically that there will be no front running if application runs on this threshold encryption protected blockchain. Now, let's discuss what threshold encryption is. The history of threshold encryption is really interesting. In many cases, mathematics starts with an abstract idea which has no use, and many years later, this abstract idea suddenly finds use. And that's what happened to threshold encryption. In 1940, there was a French mathematician that was actually trying to avoid being drafted into the war. So for actually avoiding draft, he was put in jail in France for some time. The name of this mathematician was André Weil. And while in jail, while in prison, he had nothing to do. So he came up with this absolutely abstract mathematical thing, which is now called Weil pairing, and invented this absolutely abstract branch of mathematics. 60 years later, in around 2000, 3 scientists at Stanford were actually able to use this Weil pairing, this absolutely abstract thing, to create something which is called threshold encryption. And that's something I'm going to discuss now. So what threshold encryption is? Let's first talk about regular encryption. Many of you guys probably used regular encryption in your life. You want to encrypt a document and send it to your friend, or you want to encrypt a document and then you want to protect it and later read it yourself. So you have a key, something which is called a secret key, and then you encrypt this document, and later your friend or you can actually use the key to decrypt the document. But in this case, there's just a single key, and the party you are sending this document to can decrypt the document. Now, threshold encryption is a very interesting extension of the idea of regular encryption. But for the case of threshold encryption, you actually need a group of people working together to decrypt. Let's say you have 100 people in a classroom, and all of those people have a key. You encrypt a document, and you send this document to all of those people. Now, not a single person can decrypt the document, even using her key or his key. But if 2/3 of those people, if 66 people come together, each person uses her key, and then they create some pieces of information, and they glue these pieces of information into a single document. The document actually happens to be decrypted. So someone sends you a document, it looks completely chaotic and random, it's encrypted. Then you have 100 people. Out of those people, 66 people get together. Each person decrypts the document. The decryption looks totally chaotic. And then when they take the 66 decryptions and glue them together, magically, you actually recreate the original document. It's a very interesting and strange idea. And it's interesting that it's even possible to do it. It turns that it's possible, and pretty much the only effective way to do this threshold encryption and decryption is this Weil pairing that André Weil was inventing in 1940 when he was in jail. It's really, really remarkable. So now we have this really interesting instrument where you encrypt something, you send it to a group of people. None of those people can decrypt, but only when they act together in a group, they can decrypt. It's a really interesting instrument. Now let's apply this instrument to the blockchain. When you send, let's say you're sending a transaction to a blockchain, and there are many computers in this blockchain. Let's say there are like 16 computers in this blockchain. So you're encrypting this transaction that you want to do using a threshold encryption to these 16 computers, and 11 of them can get together and decrypt. Then what's happening is that the transaction is encrypted. When you're sending it, no one knows what's inside the transaction. So no one can actually get this information, and no one can front run your transaction. Taking the example of a ticket, let's say you send a request to buy a ticket to your favorite band or your favorite soccer team, but the request is encrypted. So you're sending the request, but no one knows what's inside. No one can take advantage of this information, and no one can front run it. In the same way, you're sending a transaction on the blockchain, but it's encrypted. No one knows what you want to do, which token you want to buy, which DeFi application you want to use. So there's no one that can actually use this information to benefit. Now the transaction goes to the blockchain totally encrypted. Then, while being encrypted, it's pending. Then it's getting actually added to the blockchain. And only when the transaction is already added to the blockchain, it's decrypted using this threshold decryption and then executed. So let me repeat again. The transactions is sent encrypted. You are sending it. No one knows what's inside. It's encrypted, and then it's actually, when it's in the blockchain, it's encrypted. Now it's encrypted, it needs to be executed. So now someone needs to decrypt it. And the way it's decrypted is that out of the 16 computers in the blockchain, 11 get together, and each of them does its part of this threshold decryption. And they have this 11 threshold decrypted pieces, and they glue them as a jigsaw puzzle. And magically, you have now the original transaction, and the transaction now is decrypted, and it can be executed. So think about this as transaction being protected all the time, except the last phase when it needs to be executed. But at this last phase, it's too late for the attacker to submit a transaction, to send something, to put something in front. It's just too late to front run because it's already arrived in the blockchain. Think about blockchain is about the destination. If a car arrived at the destination, no other car can get in front of it. It's because it's already there. So the idea is that you protect the transaction through all of the stages of blockchain. When it's already at the final stage, you're decrypting it. And to decrypt it, you have the super majority of computers in your blockchain. So even if a single computer is hacked, 2 computers, 3 computers are compromised, they can't decrypt. You need to actually compromise or hack a super majority of computers in your blockchain to actually break the system. So the larger the blockchain is, the better the system is. And then because you can insert this threshold encryption totally transparently inside existing blockchain, nothing has to change. While after transaction is decrypted, you run your Solidity programming language, you run your MetaMask, you run all kinds of tools that you're used to on blockchain, and they magically work. So not only threshold encryption can magically and provably protect against pretty much all kinds of front-running and MEV, it also doesn't require you to change anything in your blockchain. It just comes for free. So you can take a blockchain that SKALE runs, and it's protected using threshold encryption. And then you can take the source code of any DeFi application you want. You can take Uniswap, you can take SushiSwap, you can take Aave, you can take anything, and you just run this on SKALE chain, and it suddenly becomes immune against against front running. So people that will use a Uniswap clone on Scale, they won't have to pay those fees to front runners. The system becomes much more efficient, and the exchange rate is becoming much more favorable for people. So it's really, really interesting technology. And it turns out that the mathematics, it looks simple. The mathematics inside is extremely complex and sophisticated. And the only efficient way to implement this group, this threshold encryption/decryption, is to use this mathematics that Andrea Weil invented in 1940 when he was in jail. That's a really interesting story, and shows how mathematics, how fundamental research can be used in a very interesting way many years after the actual person who created the mathematical object even existed. So that's a really interesting subject. And at Scale, we are using threshold encryption as a very important element of our blockchain. And the threshold encryption that we do is actually compatible with Ethereum, Ethereum mainnet, 100%. The mathematics that our threshold encryption uses can be verified using Ethereum mainnet. So Scale blockchains are going to be really helping Ethereum mainnet to create decentralized applications that are immune against front running and MEV.
That's pretty fabulous. It's interesting. I know that we're in the process right now of integrating threshold encryption into the SKALE network and using a lot of these novel approaches to old mathematics. Maybe if you could take a second, I think it would be really interesting for folks to understand, one of the approaches that you've decided to take, which is basically why create new math when there's a lot of fundamental math that's out there that we can utilize and capitalize on, that we understand and that we know how it works.
Yeah, totally, Marcus. That's totally good point. And I think, at Scale, we have people that have been doing startups for a long time. And one thing that you learn at a startup, that a startup is not supposed to develop fundamental technology. The startup is supposed to use fundamental technology that is created in academia. There's so much happening in academia. There are so many great universities. There have been so many things created in the mathematics in the past. So in many cases, it's actually a question of filtering and finding the right things to use. Cryptography, and in particular blockchain, has been so fruitful recently in using mathematics that people have been inventing pretty much like for 300 or 400 years. It's really fun to see how these people that lived, some of them lived like in 19th century and early 20th century, and many things they've done were done for fun. At that time, there was no like YouTube, there was no Game of Thrones, no TV. So mathematics just was a natural thing for people to do for fun, just not to get bored. And it's really interesting how the things which were invented solely, out of just trying to make fun and have fun, suddenly, you have this being used in this new financial world of blockchain for cryptocurrencies. It's really mind-boggling how these things are happening and how history is actually using things that have been produced many years ago.
Yeah, and it's almost funny how there's an irony in the fact that a mathematical equation that was created by someone while in jail is actually being used to stop people from doing things that are illegal. So yeah. there's a fun irony in that as well.
Lots of irony. I totally agree.
Well, anyway, I want to thank everyone for listening in. We're going to be trying to do these on a more regular basis. If you have any questions, please check out the website. It's scale.network. It's super easy. We also have a Telegram channel, Discord channel, GitHub channel. All of those will be available, when you go to our regular website. And I'd like to just thank everyone for taking the time, and you'll see more of these. Thanks, Stan.
Thank you, guys.